Welcome, curious minds, to another deep dive. We take complex research and transform it into clear, digestible insights crafted specifically for you. Today, we're plunging into a truly fascinating breakthrough in spatial intelligence. It's the ability to generate fully explorable, omnidirectional 3D worlds. And get this, from something as seemingly simple as a single image or even just a text prompt. Imagine describing a scene and then, well, literally being able to walk through it, looking in any direction, almost like you were there.
Yeah, our exploration today focuses on a technical report introducing Matrix3D. It's a new framework developed by researchers from Skywork AI and places like the Hong Kong University of Science and Technology. We'll be sort of dissecting their innovative approach. It cleverly combines conditional video generation with panoramic 3D reconstruction. And crucially, we'll look at the entirely new data set they actually had to create to make all of this possible. Our mission, really, is to help you understand how Matrix3D overcomes some pretty significant limitations of earlier methods to generate these wide-coverage, truly explorable 3D worlds. Think of it as a shortcut to understanding this advanced tech.
Right, because for a long time, the dream of generating realistic 3D worlds from basic inputs, whether it's a photo or just words, well, it's been a major hurdle for AI, hasn't it?
Absolutely.
Existing methods were often limited. They created scenes with a really narrow field of view. You could look straight ahead, maybe pan a bit, but you couldn't really, step into the scene and explore it from all angles.
That's the challenge they were up against. These earlier methods typically relied on what we call perspective images.
Okay, perspective images.
Think of it like taking a photo with a normal camera. It only captures a small slice, a narrow view. When you tried to generate a wider 3D world from that kind of limited input, you'd constantly run into these sharp, kind of ugly boundary artifacts.
Ah, right. Like the edges look weird.
Yeah, exactly. It's like trying to see a whole room just by peering through a keyhole. The edges always distort things. It brings any sense of immersion. And beyond that, previous attempts, they also struggled with visual distortions. Things like subtle wavy patterns, moire patterns that shouldn't be there, or objects incorrectly overlapping, or maybe not blocking each other like they would in real life. Occlusion problems.
Okay, so if that was the big limitation, these sort of confined, visually flawed worlds, how does Matrix 3D tackle this? What's their core innovation?
The central idea, and it's actually quite clever, is their shift to panoramic representation.
Panoramic, okay.
Instead of that narrow perspective image, imagine a full panorama, capturing 360 degrees horizontally, 180 degrees vertically, a complete sphere of vision from one point.
Wow, okay.
This spherical data, that's what allows for the wide coverage 3D world reconstruction we need. It enables true omnidirectional exploration. Matrix3D thinks about a 3D world not just as one static scene, but as a sequence of these panoramic images, where a virtual camera moves along a defined path.
That panoramic image sounds like a real foundational shift. But if you're capturing everything from one viewpoint initially, how do they ensure the world feels consistent when you start to move through it? That seems like where the tricky part is.
It is tricky, and that's where the framework's 3 stages come in. They're pretty meticulously designed. First, they take your input, text, or an image, and turn it into an initial panoramic image. At the same time, they estimate the depth of everything in that panorama, so they get a basic 3D sense.
Okay, depth map.
Right. Then, the really cool part, they generate what's called a trajectory-guided panoramic video. This is a sequence of those full 360 images, but the virtual camera smoothly moves along a path you specify.
You specify.
Yes. And what's crucial here is how they guide this video generation.
Yeah.
They use scene mesh renders instead of the older point cloud renders.
Scene mesh renders. What's the difference there?
Think of it like building the virtual scene with solid shapes, a mesh rather than just scattered points. This mesh approach, it dramatically reduces those wavy visual distortions, the moire patterns we mentioned.
Oh, okay.
And it also makes sure objects block each other correctly, proper occlusion. This leads to significantly better visual quality, makes the world feel much more real.
So they create this amazing, consistent panoramic video moving through the scene, but that's still 2D, right? A video. The goal is an explorable 3D world. How do they make that final jump, that lift from the 2D video into something you can walk around in?
Good question. To actually elevate that rich 2D panoramic video into a truly omnidirectional explorable 3D world, Matrix3D gives you 2 options. 2 distinct reconstruction pipelines. Each one serves a different purpose, really, balancing quality and speed.
Okay, this is where it gets practical. The choice between like super high detail versus getting it done quickly.
Exactly. The first approach is an optimization-based method. This one prioritizes high accuracy, really detailed 3D scene reconstruction. It takes the panoramic video, the camera path, picks out keyframes, estimates their depth very precisely. And then it uses a technique called 3D Gaussian splatting.
Gaussian splatting, I've heard that term.
Yeah, it's become quite popular. Instead of building the scene with polygons, imagine using millions of tiny, soft, sort of transparent 3D blobs or slats. These Gaussians blend together to create incredibly realistic visuals, and they've adapted this for panoramic input, which is neat. They crop each panorama into total perspective images and use super resolution.
Wow. Okay.
This method gives superior quality results. It consistently outperforms the existing state-of-the-art methods like ODGS, especially when you look at the standard quality metrics, PSNR, SM, LPIP.
Right, those acronyms, PSNR, SM, LPIPS. What do they actually tell us about the experience? How does it look better?
Yeah, good point. So basically, they measure how close the generated 3D world is to, like, a perfect version. PSNR looks at image noise, higher means cleaner, sharper. SM checks structural similarity to lines and textures match up well. And LPIPS is interesting. It tries to measure similarity the way we see it, capturing nuances our eyes pick up.
I see. More perceptual.
Right. So when Matrix3D scores better on these, it means the worlds don't just measure better technically, they actually look more natural, more consistent, more immersive to you, without those jarring visual problems.
That makes a lot of sense. Okay, so that's the high-quality optimization route. What's the second method, the faster one?
The second one is a feed-forward large panorama reconstruction model.
Hmm.
And like the name suggests, this one's all about speed. Instead of that slower optimization process, it directly infers the 3D Gaussians from something called generated video latents.
Video latents.
Yeah, think of latents as these highly compressed, abstract codes that capture the essential visual info from the video. Working directly with these codes allows for much faster 3D scene generation. Just to give you an idea, the optimization method might take, say, 571 seconds, almost 10 minutes.
Okay.
This feed-forward method. It does it in about 10 seconds.
10 seconds. That's a huge difference.
It really is. And they achieve this speed with a smart two-stage training strategy. First, the model just focuses on predicting depth. Then in the second stage, it optimizes all the other bits of the 3D Gaussians. They also use a special component, a DPT head, which helps get significantly more accurate depth estimates compared to simpler methods. That accuracy is key for a believable 3D space, even when going fast.
It really feels like behind any AI leap like this, there's always a massive data effort. And this team, they didn't just build the model, they had to build the data to train it on too, right?
That's absolutely critical. You hit the nail on the head. Existing panoramic video data sets, they just didn't have the precise camera position info, the pose, and the detailed geometry annotations. You absolutely need that stuff to train models that can generate accurate, explorable 3D worlds. So to fix that gap, they introduced the Matrix3D dataset.
Matrix3D. Okay, so what's special about this data set? What makes it work for this?
Well, Matrix3D is large scale, first off. And it's synthetic, meaning it's computer-generated, not filmed in the real world. They built it using Unreal Engine 5.
Oh, the game engine.
Exactly. Which is known for incredibly high-fidelity simulations and realistic graphics. The dataset has over 116,000 high-quality static panoramic video sequences. That's a lot. And each sequence comes with super detailed 3D exploration paths, the trajectories, and the matching depth maps. All crucial for understanding the geometry.
116,000 sequences. That's enormous. How did they even manage to build something that vast and ensure it was actually good quality and diverse, especially since it's synthetic?
Yeah, the process was really meticulous. They wanted to guarantee quality and realism, even in a synthetic world. It involved several steps. First, they gathered data from 504 different 3D scenes in Unreal Engine. Lots of variety there. Then, they sampled believable exploration routes within these scenes. They used clever algorithms, like Dijkstra's for shortest paths, and Laplacian smoothing to make camera movements smooth, not jerky.
Okay, so the paths feel natural.
Right. And crucially, they added collision detection to filter out any paths where the virtual camera would, like, crash into a wall or go through an object.
Makes sense. Avoid impossible movements.
Definitely. And finally, the quality filtering was intense. A two-stage process. It used automated checks with AI models like VideoLam A3 to spot inconsistencies, but also thorough manual assessment by humans to really confirm the dataset's high quality and consistency, making sure it was right for training.
So you put all this together, the panoramic idea, the two ways to build the 3D world, this massive new data set. What are the actual results? What can Matrix3D do that maybe other systems couldn't before?
Well, it consistently performs better, both in generating the panoramic videos and in the final 3D world reconstruction. compared to the state of the art. For the videos, it produces scenes that are visually coherent, structurally faithful, meaning the videos look good, the geometry stays consistent as the camera moves. It significantly outperforms older models like 360 DVD and Gen X, which often struggled with that kind of long-term coherence.
And for the actual explorable 3D worlds, what's the big advantage for someone using it?
The key advantage is what they call camera controllability. Much more accurate, more flexible camera guidance inside the generated scene. So compared to other systems like World Labs, for instance, Matrix3D can generate 3D environments you can navigate over a much larger range.
A bigger area to explore.
Significantly bigger. And this isn't just a small improvement. It fundamentally changes things. It enables what the researchers call endless exploration.
Endless exploration. How does that work?
Imagine you generate an initial bit of a 3D scene from your prompt. With Matrix3D, you can then decide, okay, I want to go left now. You specify a new path, and the system just seamlessly keeps extending the world along that new trajectory.
Wow. So it builds more world as you explore.
Kind of like that, yeah. It allows for these seemingly infinite virtual environments. This opens up huge possibilities, for training AI in diverse dynamic settings or creating truly immersive virtual experiences that don't just hit an invisible wall.
That sounds incredible. But, as always with cutting-edge stuff, there have to be limitations, areas for improvement. What did the researchers themselves identify as current drawbacks?
They're upfront about a few things. One is inference speed. Generating a full scene while the quality is high still takes tens of minutes, so it's not quite real-time yet for complex stuff.
Okay, so speed is still a factor.
Right. Also, the Matrix Pano dataset, while generally great, sometimes shows slightly unnatural depth transitions, especially around things like leaves on trees or gaps in fences, semi-transparent or perforated areas, can cause minor visual glitches there.
Tricky spots.
Yeah. And they also point out a more fundamental challenge. Getting super accurate depth just from those compressed video latents is hard, because the latents mostly encode appearance, what things look like, not explicit geometry. So they can sometimes affect the final render quality, especially if you need really precise 3D structure.
Okay, understandable limitations for such new tech. So, wrapping up, today we've really dug into Matrix 3D. This unified framework seems to genuinely change how we generate and interact with 3D worlds. From just a text prompt to a huge explorable space, ensuring consistency with things like scene mesh renders, the two reconstruction pipelines, it really offers a new way to navigate virtual spaces.
Absolutely. And the massive effort behind the Matrix Pano dataset, getting those detailed camera poses and depth maps, it just highlights the kind of foundational work you need to push these boundaries. This deep dive really shows how blending advanced video generation with solid 3D reconstruction leads to these incredibly detailed, navigable virtual worlds. It opens up so many doors for AI training, game development, building immersive virtual realities, fields that need sophisticated virtual spaces.
It really does make you wonder, doesn't it, how this ability to just spontaneously generate and then seamlessly explore digital worlds might reshape how we interact with information itself. What happens when the lines between our reality and these created environments can just keep blurring, keep extending? Thank you for joining us on this deep dive. Until next time, keep exploring, keep questioning, and keep being curious.